So I'm going to talk more about communication complexity, and today I want to show you where the information theory comes in. Okay, so how can you use information theory in communication complexity? The most famous example of this is what I'll start with, and that's in understanding the randomized communication complexity of disjointness. Okay, so we've seen the disjointness problem already, but let me remind you what it is. So in disjointness, Alice has a subset, and Bob has a subset of the universe, which has n elements, and they want to know, do these sets intersect or not? Okay, and actually I'll use these variables for the sets. Okay, so that's the problem, and we showed last time using the rank. You can look at the rank of the disjointness matrix, and it's full. So that means that if you want to use a deterministic protocol, there's nothing you can do besides the trivial protocol. But today what I want to discuss is what if you have a randomized protocol? What can you say then? And to understand that, what I'm going to show you, so the main theorem I'm going to prove is this theorem, which is proved by Kalyana-Sundaram and Schnittger. It says any randomized protocol requires linear communication. Okay, so even if you're using randomness, you can't really save on the communication. That's the first goal for today. This proof was. Or these proofs studying this problem was where the information theory really started to creep into communication complexity. And after that point, it was used to show many interesting things. So let's focus on this and try to see how we can show this. So the way we're going to do this is we're actually going to provide a distribution. So the way the proof will work is we'll define this distribution. So let's define two sets, x prime and y prime, and I'll think of the sets as described by binary strings, which are their indicator vectors, and I'll just tell you what their binary strings are. So the binary strings are, x1 prime, x2 prime, to xn prime, y1 prime, 2 prime, to yn prime, and they're sampled like this. You first sample a coordinate I and n at random. Okay, that's the first step. And then you sample every xj, x prime, j, the jth coordinate. You sample the sets like this. So you sample if j is not equal to I, what you do is you make sure that there's no intersection here. Okay, so this would probably do 1/3. This is if j is not equal to I. And if j is equal to I, you just sample them uniformly. Okay, so 0, 1, 0, 0, 1, 0, 1, 1, probably 1/4 if j equals I. Okay. All right. So this is I'm defining a distribution on two sets. The way you do it is you first pick a random element of the universe. this is the only location where there might be an intersection between these two sets. Okay? So everywhere else, you just sample uniformly from all the options that do not lead to an intersection. Okay? So this means the element is only in y, this is the element is only in x, and here the element is in neither. So sample uniformly from those. But in the ith coordinate, you just sample uniformly from all options, which means there is a possibility that there's an intersection. Okay? So that's a distribution on two sets. And what I'm going to prove about this distribution is that so the claim is going to be the main lemma is that this is a distribution on sets. I define these two random variables, which are two sets, and I've given their distribution here. I've defined a distribution on two sets.
Maybe the question is, well, are you using prime, x prime and y prime, and not just x and y?
Well, there's no x and y. It's just because later x and y I will spend on something else. Okay. And that the x and y will show up more often than x prime and y prime. So. Okay, so this is a way to sample two sets, and that's all I've shown you so far. Some distribution on two sets. The probability that they intersect is 1/4. Okay, and when they intersect in exactly one element. Okay, so the main lemma I want to show you is that that every deterministic protocol computing disjointness on x prime y prime with little of n error, little of 1 error, will have little of n communication. Has large error. Okay, so what I'm going to prove is that if you look at a deterministic protocol that operates on inputs that are drawn according to this distribution, then if it communicates a lot, if it sends a linear number of bits, then I can't say anything. Okay, it might solve the problem. But if it communicates little of n bits, then its error must be significant. It must have some constant error. Okay, and that immediately gives a theorem, and that's because if you have a randomized protocol that can solve the problem with omega n communication, then by repeating the protocol you can make sure that its error is really small. And then once you have a really small error randomized protocol, you can run it on these inputs and you get a protocol with small error. And then you can just fix the randomness, right? If there's a randomized protocol that works on this distribution, then just by fixing the randomness in the best possible way, you get a deterministic protocol that also works with the same error on this distribution. So you end up with a deterministic protocol that solves the problem on this distribution with small error. So and that's what I'll show is not possible. All right, so that's my goal. And intuitively, what's going to happen is, to prove this, what we're going to show is that, if the protocol is communicating much less than a linear number of bits, the problem is somehow, ahead of time, the protocol does not know what I is, right? If you told the protocol I, then it would just go and you would just go and look. You know that the only intersection can be in the location I. But you see, the protocol just sees these two sets, and we want to somehow say that if they don't reveal a lot of information, they will have very, very little information about the ith coordinate, because I sort of looks like a random coordinate to them. Okay, that's vaguely the intuition. But I want to make that formal. So that's what we'll try and do. Okay, so the way we're going to do this is, the first thing we need is a mathematical way to measure information, which I guess all of you are familiar with, but let me just remind you. So what we'll do throughout is we'll use the concept of mutual information. So that's that quantity given over there. It measures the information between two random variables that are in the same probability space. And okay, so it's always a non-negative quantity, and it's always upper bounded. It's symmetric in its two inputs, and it's always upper bounded by the length of any of the inputs. And the very nice thing about the information is that it has this nice chain rule. Okay, so there's a way to say that the information that C has about two variables A and B can be expressed as a sum of the information of the parts. So that's really nice. And another nice thing about it is that it really sort of tells you something about how independent A and B are. In particular, if A and B have small information, if the mutual information is small, then there's Pinsker's inequality, which says that that means on average, oh, this should be B. If you sample B, and then you look at how the distribution of A changes from what it was originally, that change is small. Okay? So the change in the L1 distance between the distribution of A conditioned on B and the original distribution of A is going to be small. Okay?
What is that? What do you define on A? Sum or what?
No, this is a distribution on A.
Yeah, so what is the sum?
So formally this is
F1.
Yeah, this is the L1. So formally this is, this is expectation over B, and the sum over A, the probability of A given B minus. Okay, yeah. Yeah, so by this I mean just the L1 distance of the distributions. Okay. Yeah, I realize it's confusing in this notation. Okay, throughout today, in order to save time, I'm not going to worry about the parameters too much. I'm just going to sort of claim when things are little of one, and that's it. Okay, so I won't be. So things like this square root and stuff like that, I'll just forget about it, or I'll be loose with it. But I hope you. The main goal is to give you the intuition for how the proof works, and then you can look up the details later if you're interested. Okay, so. The main thing we want to do is somehow capture this intuition that I just said, that the protocol has small information about where this random coordinate is. And that's actually quite tricky for this disjointness proof. And the way we're going to do it is actually we're not going to think about capturing that intuition on this distribution, but on a very closely related distribution. Okay? And that's what I'll say next. So let's consider a slightly different distribution. So this is the distribution on sets which are just two random non-intersecting sets. Okay, so let's define. So these are what I'll define to be x and y. Okay, so x, j, and yj are just independent and set to 0, 1, 1, 0, 0, 0 with the probability 1/3 each. So this is the distribution of two random sets that do not intersect. Okay, and the first lemma that I want to prove, that will help me prove this main lemma, is this one, which somehow is going to say, is going to capture the intuition that the players do not learn much about the ith coordinate. So I'm going to show that if you take the sum over I of the mutual information between xi and m given yi and r sub I, that's at most the length of n. Okay, so where here R sub I is going to be all the coordinates, you take all the coordinates of x that are before the ith coordinate, and all the coordinates of y that are after the ith coordinate. Okay? And the same proof will also show that the similar quantity for y is also small. The m is just the length of n. Okay? The length of the protocol, which is going to be little o of n. So what this is saying is that you take this quantity for every I and you sum them up, you get something that's little o of n. So it means for an average I, both of these quantities are little o of 1. Okay? Okay, so let me try and give you some intuition for...
Ri here is a string.
Ri is a?
Is a string.
Is a string, yes.
So we have mutual information between a bit and an n-bit string.
Oh, I haven't told you what m is. So m are the... Okay, so what we're going to do is m are going to be eventually this is going to work for any random variable m, actually. Okay, this lemma is going to hold for any random variable m that's correlated with everything here. But intuitively, to make sense of what we're doing, we're going to make m be the messages in the protocol. Okay? All right, good. Sorry, now maybe...
So on the left-hand side, you have this is for any n because that includes all of x and y.
Yeah, because the right-hand side will also get bigger. If you, it's an upper bound. It gives you something good when m is small.
And on the right-hand side, you have Ri is n minus 1 bits.
Ri is n minus 1 bits. Yeah. Okay.
And the second report, you need the same RI.
The same Ri, yes. Okay. Okay, so let me try and give you some intuition of what this is saying. So what this is saying, suppose you are Bob, right? You know the set y. Okay. In particular, you know y sub I. So this is kind of saying, typically if you pick a sort of a random I and you fix Ri, so pick a random coordinate I, and then fix Ri, which means we fix all the x values before I and all the y values after I. So that everybody knows, okay? And then Bob also knows y sub I, so he knows the y in the ith coordinate. Then the messages in the protocol teach him very little about the corresponding x sub I, which he wants to know, right? If in the protocol, presumably he's trying to learn whether what's going to happen is that the intersection that he cares about is going to be in the ith coordinate. So if he was learning whether the sets intersect or not, then when he knows yi, he needs to know whether xi could potentially be an intersecting point, especially when y is 1. That's when he really cares about it. Okay, so that's...
It's dependency across time. On the x, there is no dependency across time.
Time. There's no time here. This is all the messages. So we take the random variable, which is this entire sequence of messages of the entire protocol.
Yes, but there is no between xi and x.
This is not, oh, this axis is not time, right? This is the universe and the elements in the universe.
Okay, so there is no dependency between.
There's no dependency between them, yeah. Because, right, so here, these are all independent in this distribution. But they're not independent, okay? And that's why we need to do this trick of moving to a different distribution.
Now you consider the modified distributions.
Yeah, yeah. Here, everywhere, there are no primes. Right? It's x and y.
Something that's a little bit confusing to me is the quantification over n. So if n is really redundant encoding, so m is always a long string of zeros, and the length of m is big,
Yeah.
you might be learning something. So the bound isn't telling you.
It's an upper bound, yeah, then it doesn't tell you anything, right.
So if the messages in the protocol are somehow redundant, why does it tell me that I'm not learning anything about that?
Well, we're assuming that we're starting with a protocol which has communication little o of n. So then m will always be little o of n. So you're saying sometimes you can prove stronger. Yeah. Actually, what I'll prove is something stronger. You'll see what I'll prove. I will actually prove an information theoretic upper bound here that will actually give better bound for your example. Okay. Okay, so all right, so let me prove the lemma. The proof is actually quite short. This is not how this lemma is something that Braverman and myself came up with in a recent paper. It's so it's sort of it's short, but it's sort of a clean trick that we sort of stumble upon. So it's one of those things that's a little too clever. Okay, but it's short, so it's nice. So let's look at this quantity. So the sum over I. I'm basically just going to use the chain rule. Okay. Now the problem is, so I'm actually going to write all the. I'm going to open up the Ri. So then what you have here is x less than I and y greater than or equal to I. Okay. That's what's the quantity on the left-hand side. And I wanted to do the chain rule. I could if this thing did not depend on I. Huh? I've combined it. So this is now greater than or equal to I. This is y combined with Ri. So here it was only y greater than I. And now I have y greater than or equal to I. Okay. Now, if this thing did not depend on I, this would be, by the chain rule, this would be the mutual information between x and m combined, conditioned on y. Okay. The problem is that it depends on this y, but it's not a big problem. So what we can do is, this is at most the sum over I of the information that xi has with y less than I and m given x less than I, y greater than or equal to I. Okay, so I'm only adding more stuff, so you can only get more information. Okay, and now we'll use a chain rule. So we'll use the chain rule. So that's exactly equal to the sum over I, the mutual information between xi and y less than I, given x less than I, y greater than or equal to I, plus the mutual information between xi and m, conditioned on x less than I and all of y. Okay, so the first term is the mutual information that you get from this y less than I part. And the second term, you have to fix y less than I, or you have to take the expectation over y less than I, but then we're taking the expectation over the entire string y, right? Because all the coordinates that are bigger than or equal to I are here, and now we're also fixing the coordinates less than I. So that's what you get. And now what can I say about the first term here? Does anyone see?
It's not just some fixed quantity which is the information in one.
It's a fixed quantity, which is, but it's a quantity that we all understand very well. It's 0. Yeah. Because let's see what we have done. So we fixed here, all of these guys. These are fixed, and then we fixed all of these guys. And then we're looking at the information between xi and this random variable. But they're just independent. They're talking about different coordinates, and we fixed. Okay, so they're independent. Okay, so what we're left with is only this. No, yi is fixed. So what we're comparing is xi with coordinates that are not in the ith coordinate. and those are independent. Okay. And then this thing is just a chain rule, right? So this thing adds up according to the chain rule, so you get the mutual information between x and m given y. That's what the sum of these guys is. Okay? I can see that my plan is really ridiculously ambitious. So I give up on it. We'll just do this. Okay. Okay, so good. So this says that kind of, if you look at all information learned in this sense from every coordinate, then that's the same as the total information that Bob learns from taking part in the protocol. That's exactly what this is. This is, Bob knows Y, Bob sees some messages during the protocol, and he learns something about X. And that's an upper bound on what he learns sort of as you take the sum over I of this quantity. Okay, and certainly this is bounded by the length of n. Okay, but it's actually slightly, it's a slightly better upper bound than the length of m. It's, in fact, the fact that it's better is used in some proofs also, but nothing that I will say today. All right, so that's a really useful lemma, and now let's try and figure out what this says for our original problem. Okay, so somehow I want to relate this to the original problem, and to do that, so let's do it first. Let's first apply Pinsker's inequality to say something about what this means about the distribution of the variables when you condition on m. Okay, so what this says is that, so actually I'm going to use a shorthand, so I'll kind of write PA given B is close to PA like this to denote that they're close in L1 distance. Okay, and that'll make my life a lot simpler. So this, what this lemma, a consequence of this lemma, is that if you look at an average choice, pick a completely random coordinate I, and then sample Ri at random. Actually, sample Ri, Xi, and Yi at random. So an average choice of I, Xi, Yi, Ri, and messages in the protocol. So if you sample all these things in the protocol, then what you get is that the distribution of Xi conditioned on M, Yi, Ri. Okay, so it's the distribution of Xi when you condition all of these guys. Okay, that's like P A given B there. That's close to the distribution of Xi when you just condition on Yi and Ri. Okay? So it says basically the M does not affect Xi after you've sampled these other variables. Okay? And that means that actually if you look, so another way to say that is that the distribution of the joint distribution of M and Xi conditioned on Yi and Ri, well, that's close to the distribution. It's a close to like sampling them independently. Yes, that's right. Yeah. Yeah, so for this particular distribution, here, this thing is the same as ignoring Ri. That's right. Okay, so this is what it's really saying. So if after you sample Y and Ri, if M doesn't change that side, that means the two of them are independent. Okay? And actually you can relate this to this. It's this, you get the same error when you look at these two distributions.
Formally use Finster inequality.
Yeah. So all the errors here, the error here will be square root of the quantity you get here. Okay. Yeah. So yeah. So I'll use the. We know that the square root of the. We know that the information for random I will be this over n, and then we will have square root of that quantity. Okay, so that means, another way to write it is that the distribution of this is the form that I really want, m given xi, yi, ri, that's close to the distribution of m only given one variable, yi, ri. All right. Okay, and similarly, it's close to the distribution of m given the other variable by exactly the same proof. Oh, I meant to write here xi. All right. Okay, so so all of this is still, okay, so all of this is still about the variables x and y, and not x prime and y prime. Okay, but the two distribution, the two x and y are very close to x prime, y prime, and that's what we'll use next. So it means if you look at, so that last line means that if you look at the distribution of m given, so I'll write here xi, yi, ri, and okay, so I wrote there that it's the same as the distribution of m given yi, ri. Now, if this equation holds on on average, that means that if I condition on, say, if I condition on these things being 1 and 0, that'll also be close to this being 0, right? So these things are true on average, and xi and yi take on the value 1, 0 with probability 1/3. Okay, so there cannot be a large distance between these two distributions because up to a factor of 3, the error would apply also to the previous bound. Okay, so you actually get that even after you fix these to these values, you have that these two are close. But by exactly the same argument, that must be close to the distribution of m when you set xi, yi to be 0, 0. Okay? Because, I could have picked 0 instead of 1 here. And then I would have got 0, 0 is close to the same distribution here. Okay? So now we're getting something interesting. Okay? So now it says the distribution of m, whether you have 1, 0 or 0, 0, it looks the same. And by exactly the same argument, you get that the distribution is also the same if you have the remaining choice. Okay? So no matter how you set xi and yi in this distribution, you get the same induced distribution on the messages. And the point is that the distribution here, all of this would work if I put primes here, right? Because you see that once I fix xi and yi to be 1 and 0, the joint distribution of all the other variables in the two probability spaces is the same. Right? Once you condition on the event that the two sets are disjoint, x prime and y prime has an identical distribution to x and y. Okay, and that's why x and y is very useful to understand that. So once I've conditioned, so this enforces that x and y are disjoint. And now that means that if I have that bound, I can now switch everything to the primes, And now I got something about the actual distribution that I cared about. Okay. So I put primes here everywhere. All right. Okay, so what I want to say, so here's a whole bunch of distributions that are all the same. What I would really like to say is that these distributions are also close to m prime given xi prime, yi prime, ri prime equal to 1. Okay? And then I would be done, right? This is what I want. Okay, so so far I got that when the inputs are 1, 0, 0, 0, 0, 1, the messages of the protocol cannot tell which case they're in. They look all the same. But the protocol is not required to do anything differently on those, right? Because it's supposed to just output disjoint on all those cases. It's supposed to output not disjoint only in this case. Okay, so I now need to somehow prove that these distributions are also close to this, and then I'll be done. That will show that the protocol is not working. Okay, and so far, actually, everything I did not use the fact that M was a protocol anywhere, and this is where I need to use the fact that it's a protocol. Intuitively, because M is a protocol, comes from a protocol. You know, when you fix M, protocol, you know, rectangles have this nice property, right? If you have the points 0, 0, 1, 0, and 0, 1, and then you also must have the point 1, 1. Okay, and that property is going to be useful to show that also if these three distributions are close, then so is this distribution. Okay. Okay, so formally, the way you do this is by looking at so actually I should say, so after you bound this information, there are multiple ways to complete the proof. And I'm showing you one that I like, but there are many other ways to reason to get a contradiction from this point. But the way I want to show you is you use the Hellinger distance. So I'll tell you what that is. So the Hellinger distance between, so suppose you have distributions, you know, so P1 through Pn, or P1 through Pt, Q1 through Qt, then you can look at this quantity, which is the sum over I square root of Pi minus Qi squared. Okay. So this quantity is equal to, so one way to write it, so if you just open up the square, what you get is the sum over I Pi plus Qi minus 2 square root Pi Qi, which is equal to 2 minus 2, this is the sum over I. Okay. Okay. The moral of the story. So this is a measure of distance, and what it looks like is it's one way to write is it's 2 minus 2 times something that depends only on the product of the probabilities for every point. Okay, that's going to be crucial, and this is actually a good approximation for the L1 distance. So on the one hand, you can show that it's upper bounded by the L1 distance. Okay, and it's also lower bounded it's lower bounded by the square of the L1 distance, I think. So I think it should be 1/4. Okay, I might be wrong on whether this 4 is inside or outside. Okay, anyway. Okay, the point is that it's lower bounded by roughly the square of the L1 distance, and it's upper bounded by the L1 distance. Okay. So what I want to show you is that for protocols, you must have the feature that the distribution of m prime so I claim the following. Bear with me while I write this long equation out. Okay, so this is what I claim. Okay, so this is a claim that applies to private coin protocols. So if you have a private coin protocol, then it has the following feature. The probability that you see the sequence of messages m prime, given that the inputs are 1, 0, times the probability that you see the same message when the inputs are 0, 1, that's equal to the product of the probabilities of seeing 0, 0, and 1, 1. Okay? And so let me tell you, let's think about this, so intuitively, let's think about the first message in the protocol. So imagine that the protocol is just one message. So in that message, say Alice is speaking first. So Alice sends this message. Now, if Alice has a 1, the probability that she'll send this message is exactly this number, because it doesn't matter what Bob's input is. If Alice has a 0, the probability she'll send it is this. So this is the product of the two probabilities that apply to Alice. And the same is true of the right-hand side. If Alice has a 1, she'll send it with this probability. And if she has a 0, she'll send it with this probability. So there's, this term is equal to this term, and this term is equal to this term if Alice is speaking. And after you condition on the first message, if Bob is speaking, this term is equal to this term, and this term is equal to this term. Okay? So for every message, there's sort of a matching between the two terms. Okay, and so that's one, that's an equation way to write it, but really what's going on is this intuition. Okay, so kind of, if you have this and this, you're going to have this and this. Okay, that's another way to write that. Okay, so, but what does that mean? It means that the Hellinger distance between these two distributions, that's determined by these products, right? For all m prime. It's determined by these products. So it's actually exactly equal to the Hellinger distance between these two distributions. Okay? So the Hellinger distance between these two is the same as the distance between these two. And that means, because Hellinger and L1 are related to each other, you can go back and forth between them. The fact that these three are close, in particular, that means the 1, 0 is close to the 0, 1. And therefore, the 0, 0 must be close to the 1, 1. Okay? So we get that the 1, 1 is also close to these three. And that shows that there's no protocol that can solve this problem with small communication. Okay. In fact, it shows something stronger, actually. It shows that, it really shows that, if you feed this hard distribution in, the distribution of the messages have no information about the actual interesting coordinate. Right? The messages are have close to the same distribution, no matter what the setting of the interesting coordinate is. Okay. All right. Okay. So, any questions? Okay, so that's a proof of the lower bound for why disjointness requires linear communication. And this is a really nice proof, and it also suggests a very natural quantity to study for protocols, and that's what I want to explain next. And I'll explain it by talking about the problem of computing direct sums, of proving a direct sum theorem. So what's a direct sum theorem? It's a theorem that looks like this. So here's a theorem. So the theorem says, suppose f of xy requires C bits of communication in the randomized setting. Then to compute f on n independent inputs, so imagine you want to compute f of x1, y1, f of x2, y2, f of xn, yn, requires c times square root n divided by log of c times square root n bits. Okay, so this is a theorem that we know how to prove. It was proved a few years ago by Braverman, Barak, Chen, and myself. And that's still the best bound we know how to prove for such a theorem. Okay, so intuitively it's asking, if you have a function that you want to compute and you have found the best protocol for computing that function, and that takes c bits, what's the best protocol for computing n copies of that function on n different inputs? Like naively, you could just run the same protocol on n different times. That would take n times c bits of communication. But can you do better? So today we know that there are examples where you can do it in maybe c times n over 10 bits. Okay, so there are examples where you don't need to spend c times n bits to do n copies. But we still don't know, exactly how much you can save. There's still a gap, and this is the best lower bound that we have. But I want to tell you, so how do you prove such a thing? The proof, at least part of the proof, looks quite similar to what's going on over here. What we do is we look at, okay, so we have, the first thing you can do, you can say that if f requires c bits of communication, then there's actually a hard distribution on the inputs that requires c bits of communication. Okay, that's something you can prove by von Neumann's min-max theorem. And once you know that, you can look at the distribution x1, y1, just take n copies of that hard distribution, and we're going to try and show that that requires that number of bits of communication. Okay? And intuitively, or the way we're going to try and do that is we're going to apply the same lemma that we wrote here. Okay, exactly as it's written. So take n copies of the points in the hard distribution and apply that lemma. Okay? So what that lemma says is, it says that if you look at the sum over I, xi m given yi ri, then this is bounded by okay, so say m is a protocol with L bits of communication. Then the lemma says that this is bounded by L. Okay? That means for an average choice of I, the amount of information that Bob is learning about the input xi that's related to the ith coordinate is like L over n. Okay? So intuitively, Bob is, so here's now the plan. Okay, so we do this for both, so we pick an I where both this quantity and the corresponding quantity for Alex are bounded by L over n. And once we have that coordinate, we just imagine fixing our I, and now we got a protocol for computing f, just one copy of f, in the ith coordinate, where the protocol still takes L bits of communication, but the information that Alice and Bob learn by participating in the protocol is L over n. Okay? So that seems strange, right? The protocol is communicating L bits, but it's learning very little information, L over n. So that's the first step. And then the next step, what we do is we show that you can compress. So we compress this. And we show that you can actually get a protocol with L over square root and log L bits of communication. Okay. So in general, what we do is we discuss the problem of compressing protocols. So for any protocol, you can talk about the information of the protocol, which is exactly the quantity that you see here. It's the amount of information that Alice learns about Bob's input and Bob learns about Alice's input when they take part in the protocol. And then what we show is that if you have any protocol that has I bits of information and L bits of communication, so I info and L communication, you can compress it to get a protocol which has communication that's like square root of I times L times log L. Okay? And that's exactly what you get when you apply that compression protocol to this protocol. All right, so I won't have time to explain the compression, but it's a fairly simple protocol. Yeah. Why doesn't the linear lower bound? So there's a big difference between these two worlds. So here, the information that you get, so for an average coordinate, the information you get here is much less than 1. Right? So information is much less than 1, that means these distributions are close. Here, what's going to happen is you'll get L over n. L is something like that number. It's not going to be less than 1. It's going to be large. Okay? So none of the distributions, it's not true that the distributions are just close. You can't just ignore the inputs. So you actually need a protocol where you are sending information about the inputs, but you just want to send a few messages and a few bits. Okay? That's why the two problems are quite different. So the first part is the same, but then somehow you want to use the information bound, which is not less than 1, to actually get a protocol that's efficient. Okay. So there is something non-trivial in this compression. You can't just move to saying that the inputs are sort of irrelevant. But we managed to do it, and then when you plug this back in, what you get is that this means that this number must be at most must be at least C, because that's how much communication it takes to compute the function f, and that proves the bound that I wrote there. Okay, so I will. So I'll just say briefly that since then, what's happened is so then that led to the question of, in general, if you have some measure of how much information you're learning from a protocol, how well can you simulate that protocol? Okay, that's a general question, and there's been a lot of work on that. So this is one compression method, and there's at least 2 or 3 other ideas that give various parameters for compressing protocols. And there's even a couple of different ways to measure the amount of information that's learned in a protocol. So one way that you can measure things is, instead of measuring this, which is this quantity is what we call the internal information of the protocol, you can also measure the mutual information between both inputs and M. This is kind of what an external observer would learn from watching the protocol. And actually, this we can compress much better. So we can give simulations that are much closer to the amount of information that's revealed in the protocol. Okay, but I won't have time to tell you about any of that. So I'll stop here. Thanks.